know if everyone is doing galaxy clusters, so I try to do like an introduction that is not that basic, but I apologize if I am repeating some things that you already know. Um, all right, so let's get started. Um, so as you know, when we observe galaxy clusters in the radio band, we observe this diffuse radio emission that doesn't necessarily come just from radio galaxies, but could also have its origin in the intracluster medium, right? We have these guys over here that we call, for example, radio relics that tend to be in the outskirts of these galaxy clusters. And due to their properties and also, their shape, their elongated shape, and arc shape, we inferred that these are being light up in the radio band because they are tracking merger shocks that are propagating in the ICM. On the other hand, you know that we also observe this diffuse radio emission at the center of galaxy clusters, and these guys over here, we call them radio halos. Now, right now, there are a lot of new observations with higher resolution, and you can go even deeper. And I think like these type of namings will start to become a little bit tricky because what we are starting to see is that basically all galaxy clusters are filled with these electrons that are emitting in the radio band, right? So we're gonna start to see complicated things from now on. And just to illustrate that, uh, I'm gonna give you a couple of examples, which maybe some of you already know. So this is a radio observation from Able 520. This was an old observation with the VLA. And here, this blob over here, it was already cataloged as a radio halo. But now with Meerkat, things are changing a lot, right? And so we are starting to see a different picture about these galaxy clusters. And so as I was telling you, then we're starting to see that basically the whole cluster is filled with this diffuse radio emission. Another thing that we are also starting to see that is kind of new is this example over here. So here you can see an observation of the Perseus cluster. This was observed by Reinout van Bern with LOFAR. So probably you also are familiar with this observation. And basically here in this new observation, what they detect is a giant radio halo. And so before we tend to think that these giant radio halos would be mainly found in merging galaxy clusters, right? But this is pointing to the fact that, okay, maybe these giant radio halos are gonna start to be relatively common also in cool core clusters. It's just that, before we didn't have the capability of just seeing that emission extending to larger scales. Um, and so, of course, what we want to understand is what is happening then with magnetic fields and cosmic ray electrons such that we understand this diffuse radio emission. And during this talk, I will be mainly talking about the cosmic ray part. And here we are interested in knowing what are the sources of these electrons and what particle acceleration mechanisms explain these observations. Now, probably some of you have already heard about these particle acceleration mechanisms, right? So in terms of radio relics, people talk a lot about this diffusive shock acceleration mechanism. In terms of radio halos, people talk about turbulent reacceleration mechanisms. And I just want to remind everyone why we even talk about these particle acceleration mechanisms. So when we take a look to the typical diffusion scales of giga-electron volt electrons, we find that that scale is considerably smaller than the megaparsec scale of the emission that we are observing, which is pointing to the fact that we need some sort of mechanism that is continuously accelerating the electrons to maintain them at those energies such that we can observe them in the radio band, or that these electrons are being produced locally. Now, even though we have these particle acceleration mechanisms that people talk about, there are still some things that we do not understand. And in the next slides, I want to tell you a little bit about the problems that we have with both of these mechanisms. So in terms of radio relics, here we always talk about the diffusive shock acceleration mechanism, or DSA for short. So here there are two possibilities. We talk about the fresh injection model or reacceleration model. In the fresh injection model, we are thinking about a thermal population of electrons, which we know for sure that exists in the intercluster medium, right? And then we are thinking about the possibility for these thermal population of electrons to be injected into the DSA mechanism. Now here, I want to remind you that it's not always so easy for a thermal population of electrons to be injected into this DSA mechanism because there is an injection energy required for the electrons to enter into this DSA mechanism. And this tends to be especially a challenge when you have really weak shocks. So in galaxy clusters, as maybe you know, the shocks tend to be really weak. And when they are like especially weak, like below 2.3, a Mach number of 2.3, we don't really know how this population can be injected into DSA. And also, if you think it from the side of just radio observations, when you take your formula from DSA, right? And you try to work things out such that you can explain the radial luminosity that you are observing, you basically need shock acceleration efficiencies that seem to be rather high, that seem to be comparable to, for example, shocks that are really strong in like if you think about shocks in supernovae, right? So this seems to be kind of like in conflict. And so that's why people tend to talk about this other model, the reacceleration model. And here people are thinking about the possibility of a fossil population of electrons lying around somewhere in a cluster, such that when the merger shock crosses that cloud, then these electrons have already a higher energy such that they can be injected into the DSA mechanism. Now, in terms of radio halos, here we also have two different models. So the first one is the secondary cosmic ray electron model or hadronic model. So we know that, well, we are expecting to have a lot of cosmic ray protons living in galaxy clusters, right? And if that is the case, they should be also interacting inelastically with thermal protons. So proton-proton collisions can give, as a decay, charged pions and neutral pions. And so the final outcome of this decay over here of the charged pions will give birth to secondary electrons, which in principle can contribute to your radio halo emission, right? The problem right here is that you would also produce neutral pions, which will decay to gamma rays. And of course, as we know, as of now, there is no really firm detection of gamma ray emission in galaxy clusters. So that's why people tend to talk about this reacceleration model. So here, the idea is basically that you would have electrons that are being accelerated through the scattering with MHD turbulence. And there have been a couple of mechanisms that have been proposed in the literature relying on different types of turbulence, namely, for example, compressible turbulence or incompressible turbulence. Now, the problem with these reacceleration models is that these are Fermi-2 type of mechanisms. So that means that this mechanism would be inefficient for thermal electrons, right? And so for these mechanism to be efficient, what you need again is a fossil population of electrons. So here I'm trying to summarize all of these problems, right? So we seem to have some theoretical background for what is happening both in radio relics and radio halos. We have particle acceleration mechanisms that we think they could work. A common problem is that it seems that these mechanisms are efficient for accelerating electrons from the thermal pool. And a common solution for that has been to have a fossil population of electrons. But where could these fossil population of electrons could come from? Well, basically, we could have a fossil population of electrons if there were previous episodes of acceleration, or we could have them originating from a local source such as AGN. And so that is a possibility that we wanted to explore with this work. So we carried out a parameter space study of AGN jets in clusters that are undergoing a binary merger. So what we did in this work was to work with idealized MHD simulations. So what I have is two galaxy clusters, and basically I smash them onto each other. And in addition to that, what I have is that at the center of the most massive galaxy cluster, we have a black hole particle, and then we have a jet model that will inject a bidirectional jet. And the energy in the jet will be in the form of kinetic, magnetic, thermal energy, and also cosmic ray energy. So that means that on top of the MHD, we are also having cosmic rays. And so for that, we use the two fluid approximation. So just to give you an idea, the type of things that we have been looking at here, I'm showing you some videos. So you are seeing here the projection maps of the density, magnetic field strength, and here on your right, the cosmic ray pressure. So some things that we wanted to vary in our simulations were some parameters on the side of the merger itself. So we tried different mass reaches of the merger, and we also tried different impact parameters. And in terms of the jet model here, I should mention that we have a simplified jet model where I am able to select the initial power of the jet, and I am working with a single outburst. And so parameters that we were interested in taking a look at were what happens when I initialize the jet in a different direction, what happens when I turn on the AGN at different times, and also what happens with the duration of the outburst. And on this side over here, you're seeing basically the main thing of the simulation. So you're seeing how this single outburst is being generated, and it's injecting cosmic rays into the cluster environment. And on blue here, you're just seeing the shocks from the merger. And you're seeing how a merger event is really efficient for dragging out all these cosmic ray material to very large radii. And effectively, what you end up with is with kind of like a roundish morphology at the center of the most massive cluster. Um, and that is, permeating a very large extent of the cluster. So, some questions of interest that we had was to take a look to what do we see some resemblance with morphologies from observed radio galaxies? What is a typical radial extent reached by this cosmic ray jet material under a merger? And then we know that this material, if there is no reacceleration happening, it will just cool down, but at some point it would just become a fuzzy population of electrons, right? So we also wanted to know, could this fossil material be reaccelerated somehow, either through shocks and turbulence? So the first part of the evolution, of course, is the disruption of the AGN lobes. And here I'm showing you in the top panels, again, the projection maps of the density. And in the lower panels, you are seeing the projection maps of, again, the cosmic ray pressure. And as you can see already from here, the cluster environment and its dynamics will be really key to shape the morphology of the material for all of the cases. And you basically can obtain a plethora of morphologies just with a merger. And just to illustrate a couple of things, so there are cases, for example, where we see sources that look like this, that kind of like resemble the morphology of wide-angle tails. We obtain things that kind of like look like this, which reminded me to, this S shape that was observed by Bruno et al. In 2019. We also observed things that look kind of like the source that I found in the lot survey, where you have basically like a tail that has been disrupted, or and it's kind of like wobbling. Um, and so this is something that we didn't really go into deep within the paper because it was already too long. But but now we are starting to take a look to specific cases within all of our simulations. So for example, we are starting to take a look to those simulations where I see that the morphology is somehow resembling a wide angle tail, right? And what I can tell you is that so we have a total of 48 simulations, taking into account all of the variation of the parameters that I told you about. And for example, for these specific type of sources, I am just seeing them forming in specific cases, and that is only about 6 simulations in the sample. Now, moving on to the second phase, right? So here we are talking about the phase where all of the cosmic ray material has basically been dragged out and mixed with the intracluster medium, and is having a shape that looks kind of like this. So we were interested in knowing, okay, so what is the typical radial extent that this material could even reach, right? So I am showing this plot over here. So you're seeing here the radial extent in the y-axis, and in the x-axis you are seeing time. Now, different panels over here are just different simulations where I turn on the AGN at different times. And so if you pay attention to, for example, the first two panels, so here I'm having cases where the outbursts happen before the second core passage. And in this case, it is possible for the cosmic ray jet material to be dragged out to very large radii, so reaching of the order of megaparsec scales. And in contrast, if you're having an outburst that is happening after the second core passage, the material can stay more confined towards the center, and then it will reach smaller radii of the order of 400 kpc, right? So one cannot help to think about, for example, like when you have something that big, you can think of morphology of a radio halo, right? And when you see something smaller, you can think of a mini halo type of morphology. Now, the next thing that we wanted to check was what's happening with the shocks, right? So like, could they somehow reaccelerate these fossil population of electrons? So here we did a simple test. So we have a shock finder in our simulations, and we just took a look to the results of that. So what you are seeing here is a plot of the mean Mach number detected in a total sphere of radius of 5 megaparsec scale. So these are all the shocks within that sphere. And as you can see, the mean Mach number is usually not that high in any case. So depending on the mass ratio, you could get a maximum of 3.5 or 2.5. So this is still rather low. Now, these are all the shocks within the box, right? But I want to see like, okay, but what's happening with the parts of the shock that are actually touching the cosmic ray material? So we did take a look to that, and for almost all of the simulations, basically, here the mean Mach number is rather low. It's of the order of 1.5 to 2. So in this case, it seems to us, or well, we concluded that it will be not necessarily a large contribution if these electrons will be accelerated by shocks. Is there a question? Oh, do you want me to answer now, or do I answer at the end?
You can answer in the end. Thanks.
Oh, okay, cool.
Yeah, up to Paola. Yeah.
Okay.
I'll just ask 3 to accumulate questions, but you can answer 10 if you prefer.
Okay. Right. And so, yeah, so this mean Mach number here is rather low. And there is another thing that is really uncertain in terms of plasma physics. Okay, so in terms of plasma physics from simulations that are peak or hybrid kinetic, it is still not clear how you can inject these electrons into the DSA mechanism when you have shocks that are really, really weak. And it doesn't matter if they are thermal or they are fossil. So as of now, it seems to be that there is a critical Mach number below which the injection into DSA is not happening. And so this critical Mach number is actually 2.3. And what we are detecting in our large scale simulations is just lower than that. So, so in this case, we cannot really make a strong conclusion that the strength of the shock could accelerate this fossil population of electrons. Now you might think like, okay, but this also depends on the configuration that you are having, right? Like where is the material and when is the merger shock happening, right? So So there are a couple of things, right? So first you can think like, okay, what if the cluster was already filled with this fossil population of electrons everywhere, and then you have the merger, right? Because then I will have that basically all of the shocks that are generated could accelerate the electrons if they are strong enough. So that is like one possibility, yes. And another possibility is to take a look to what happens if the contribution of an AGN is not necessarily just at the center of the cluster, right? So what happens if you have a radio galaxy somewhere far away from the center? And this is something that is really preliminary, but we are trying to take a look to that as well. As you can see over here, this is again the cosmic ray pressure projection maps. So this is really preliminary, but we are starting to see a couple of things. And the first one is that basically there will be, yes, preferential locations at which you can have that the cosmic ray material will interact more with the merger shock. And another thing is that in contrast to the other simulations that I was showing you, it is not always necessary, or it is not always the case that all the cosmic ray material will end up permeating the central region of the galaxy cluster. Now, going back to the simulations where I just have a central AGN with a single address, right? The last thing that we wanted to take a look at was to, okay, what if this fossil population of electrons is being reaccelerated by turbulence? And so in the literature, there have been a couple of models suggested. In our simulations, we basically took a look to one of them, which relies on super-Alfvenic incompressible turbulence. And here the basic idea is that electrons could be reaccelerated if they interact stochastically with regions of reconnection and also dynamo. And the final outcome of that is that the particles will undergo some acceleration that resembles a Fermi 2 type of mechanism. And here there is a key assumption, and that is that the effective mean free path of the particles could be as large as the Alfvenic scale. Where here, I'm going to define the Alfvenic scale. So that is the scale at which your turbulent motions, the velocity of your turbulent motions becomes comparable to the Alfvenic turbulent motions. And so this is apart from theory, right? So what I care about in my large-scale simulations is to take that theory and convert that into a subgrid model. And what I care about specifically is to take a look, okay, what is the acceleration time associated to that turbulent acceleration mechanism? So basically, I take the outcome from theory and I compute the acceleration time at all of the cells within my simulation. And why do we care about that? Well, here I am showing you the typical cooling timescales for electrons. So you know electrons will lose energy through synchrotron, inverse Compton, Coulomb losses, and Bremsstrahlung. And if we are caring about the radio, we are taking a look to electrons with Lorentz factors of the order of 10 to the 4, right? So what we want to know is how efficient would this mechanism be, right? So if it's efficient, then the acceleration time should be faster than the cooling time of the electrons. So we want something that would be lying down here. And So there is a thing that we don't really know because there have been no proof of what's happening in the intracluster medium, basically, and that is the exact mean free path of the particles. So in our case, we leave that as a free parameter. So as I told you, the maximum mean free path of the electrons could be this Alfvenic scale, but it could be lower than that, right? So what we do is that we just take percentages of scale. And just to illustrate how things can change a lot, here I am showing you like, okay, what if you assume that the mean free path of the electrons will be just 10% of this Alfvenic scale. So in this case, you end up with acceleration times that would be really, really short. Whereas if you assume a 50% of that scale, then you start to see how the acceleration times associated to these mechanisms start to be comparable to the cooling time of the electrons. And so we do this exercise, but with all of our simulations and as a function of time. And basically, since we are able to do that in all of our cells where we know that we have cosmic rays, at the end, what we care about is to know like which is the volume fraction, right, of that material that can be actually reaccelerated. Because also radio halos are thought to be volume filling. So this is something that should be relevant. Okay, so I'm showing you here an example of such type of evolution. So here you are seeing the mean volume fraction at which this turbulent reacceleration mechanism could be efficient as a function of time. And there are a couple of things to see here. The first one is that this mean volume fraction is not a constant. It will definitely have certain evolution, and that evolution is dictated by the cluster environment itself. So for example, if you take a look to these pink shaded region, here is a period of time where there is the first core passage happening. So basically here you are having a lot of just bulk motions and shocks, but you're not having really a lot of turbulence. And so here you can see that the mean volume fraction will drop basically to 0. Meaning that this mechanism will not be effective during those periods. Now, afterwards, what's happening? So afterwards, we have the generation of sloshing motions and also turbulence, right? And these really promotes the velocity motions that we want for this mechanism to work. And so this is what is shown here in the purple shaded region. Now, finally, so I just want to say that this is a particular mechanism that we took a look at, but again, there are a lot of specifics within the model that we don't know in reality, right? Because we cannot observe such type of plasma in any experiment here on Earth. So like, and there are many things that we still do not know about the intracluster medium, right? So, and one of the things about this model is like, okay, you don't even know what's the mean free path of these particles. So that's why we wanted to, constrain these with our large scale simulations. This is the last part. So here I am showing you basically the same plot that I showed you in the previous slide. But here you're just seeing a bunch of different simulations. So again, in the y-axis, you are seeing that volume fraction as a function of time in the x-axis. So what I'm gonna do is that I'm gonna show you with blue shaded regions the periods at which I consider that this particular mechanism will be efficient. given a certain assumption in the mean free path of the particles. And I'm calling the mechanism to be efficient if I have that the mechanism is accelerating at least 50% of the material. So let's start. So what if you consider that the mean free path of the particles is just like a 10% of the Alfvenic scale? So here, as you can see, I'm like putting here in blue almost like the same periods of time for all of the simulations. And so what's happening here is that if you consider that, the acceleration can stay active for 2 long periods of time. This will be of the order of 5 to 7 gigayears. And what you also have is that almost all of your cosmic ray material from the AGN, in principle, could be accelerated by this model. Now, is this realistic? Obviously, no, because if that were to be the case, then we would be observing radio halos in every single galaxy cluster. And what we found out to be a more adequate constraint for the mean free path is this value over here. So as you can see already, these blue shaded regions already changed, right, in comparison to here. So, and they will change according to what is happening within each cluster, the dynamics and the turbulence mainly. And you can see how in some cases you even have not just one long period of time, but you could have even like 2 periods of time at which this acceleration can stay active. So what you're having is more reasonable because here you're having that the acceleration can remain active for shorter periods of time of the order of 1 to 3 gigayears. And then in this case, what you would have is that the cosmic ray material could that will be accelerated will be of the order of 20 to 70%. And so these, I wanted to add finally that these periods of time have been also in the ballpark of what one can get with other methods, namely taking a look to the radio spectrum. So as you know, in radio halos, you have a curved radio spectrum. And basically, the explanation of that curvature can leave you to know a little bit what should be the time frame at which the reacceleration has been active. And so this has been done by other groups, right? And they also think that they need that the acceleration should be active for at least like 1 to 3 gigayears. And so I think with that, I will try to just grab everything. So what I showed you here is a study of idealized galaxy cluster mergers, where we have an AGN at the center of the most massive galaxy cluster. I showed you how a merger is really effective to disrupt AGN lobes and also to afterwards drag out the material to very large radii in a way that it can permeate the whole central region of the cluster. We also talk about the possibility for this material to be reaccelerated by shocks or turbulence. In terms of shocks, I showed you that basically the mean Mach numbers that we are getting are really low. So we didn't conclude that there was going to be a significant contribution in this channel. So one thing that we want to do next is to take a look to off-center outbursts, and also multiple outbursts could also change this picture. And finally, we also took a look to the reacceleration by turbulence. So here we only took a look to one specific model And we concluded that yes, it could be effective, but as you saw, this really relies on like tuning down certain parameters, namely the mean free path of the electrons. So what we want to do next is explore other turbulent reacceleration models that have been proposed in the literature, and also go further and model the synchrotron emissivity by using Fokker-Planck solver. And yeah, with that, I would like to thank you for your attention.
Thank you very much, Paola. Virtual applause. That was very interesting and very comprehensive. We already have one question in the chat, so maybe Keegan can start, and people, please raise your hands for further questions. I guess Patty is next, but Keegan's question first.
Yes, so here, what's special about the 6 simulations we use event AGN? Yeah, that's a good question. So what I'm seeing is that I'm seeing those morphologies only when I have that the AGN is turned on almost almost at the beginning of the simulation. So the outburst has to happen before the first core passage. And another interesting thing that I am seeing is that I'm just seeing that for a specific impact parameter of the merger. Yeah, I don't know if that answers your question. Keegan?
Yeah, can you hear us now?
Yeah.
Sorry, yeah, you
okay.
said thank you. We turned it off to avoid feedback.
Okay. Yeah.
Okay,
Then I don't
Patty,
know
you had a
what.
question?
Yeah.
Yes, thank you very much, Paola, for a great talk. Very interesting. I think I missed it somewhere, or maybe you didn't mention it, but what role does magnetic field amplification actually play in this process? Is it just mergers and the magnetic fields aren't doing anything, or do they play a role at all?
Yeah, so here, yeah, that's true. I didn't really mention that. How do I go back? So they do play a role, and I didn't talk about that a lot, but wait, I cannot move this. Okay, now. Yeah, right. So we start with a magnetic field that is already random. And you can see that actually the merger, I don't know if you can see it here, but it does stretch the magnetic field lines, and it will amplify the magnetic field.
Okay.
Now, in terms of how these will change things in terms of the last part of the talk, the turbulent reacceleration part, I didn't kind of like took a look to specifically what happened like with the amplification itself, but we have to take the magnetic field information, because I took a look to the typical synchrotron losses, right? And so for that, you need to take a look to the magnetic field strength at all of the points in the simulation. So that definitely plays a role there. And as well, in the part where, so this turbulent acceleration mechanism, so you need to compare with the Alfvenic velocities. So also there it plays a role, because, the Alfvenic velocity, for computing that, you need to know the magnetic field strength. In terms of the first phase of the evolution, so for the disruption of the AGN lobes, so here we didn't really take a look to different magnetic field configurations, right? So we could actually try to crank up the initial magnetic field within the AGN lobes and see how that affects on the way how the lobes are being disrupted. But here we didn't take a look to that.
Okay, yeah, that would be quite interesting to actually see whether you get more
Yeah,
acceleration with. Okay, cool.
yeah.
Thank you. Thanks.
Okay, thanks. I think Brian had his hand up and then Najim. Brian, you want to ask the question?
Hi, estoy here using Brian's computer. So I think we can continue with the simulation. My question is about exactly here. I understood that here in this simulation we have AGN in the center of the cluster. I don't know if I'm wrong, and I can see some kinds of shark near to the center of the cluster or near to the AGN, and I know that the relics are generated by these kinds of sharks, and my question would be like why we don't see such kind of relics in this area of the center if we have some kinds of sharks or we have sharks. Yeah.
Right. Yeah, so that's a good question, right? So, my answer to that, and I think like in cool core clusters where you have, the AGN at the center, you mostly don't see radio relics, right? You would see radio relics when you observe merging galaxy clusters mainly. So this is the part that I was trying to explain here. So, the shocks that we are observing that interact with the AGN material, they are basically really, really weak. So I am thinking that basically just they are that weak that there will be no significant energy for them to be injected into DSA. So that's why we don't see them. Yeah, I don't know if that makes sense to you.
Okay. Thank you.
Thanks. And Najim, you got your hand up?
Yeah, thanks. Thanks, Paula. Paula, in your key takeaway slide, you mentioned about the first one, okay, where the AGN jet can grow to megaparsec scale. Is that correct?
Yes. Yeah.
Okay. So then my question is, there's still a big debate about giant radio galaxies in a cluster environment and how the environment impact the creation of the GRGs. How does your work, I don't know if you look at that, align with models of GRG? Because it seems that there are some kind of like overlap between what you have done and what other people, okay, are doing modeling GRG. So have you thought about that?
Not really. Could you tell me what they are specifically seeing?
Yeah, I mean, there are different web models that people are using
Mm,
to explain the formation of GRGs, but I don't think when they do their modeling, they put the cluster environment as one
okay.
of the parameters, okay, as you are doing. So that's why, okay, I would be interested to see now to compare your simulation with no cluster environment and then see if the environment, okay, does actually has a big impact on those GRGs.
Oh, okay. Yeah. So I guess that will depend on like the parameters that you will put in terms of like the energetics that you initially put in the jet model. right?
Mhm.
There is already a work with a cluster environment where there is no merger.
Okay.
So that has already been published. And that does affect a little bit the morphology of the lobes, but I think that I mean, like, I didn't vary that many parameters in terms of the gen model itself, which I could potentially do next. But like what I'm seeing is that the cluster environment, like if you have a merger, the merger is really, really important. Like it will really dictate the final morphology that you would get.
Okay. Yeah. Thank you. I may have a second question. I don't know if there are other people who are willing to ask a question. Oleg? Okay, I guess I'll go with the second question. We have also
Sorry,
seen
Nadim, I've got a
that.
question in the chat.
Oh, okay. Sorry, Catherine. Go ahead, Catherine.
Yeah, it's just it's actually linked in the chat. It's a paper, a Nature paper about jets in ABEL 3376 that deals with a kind of 90-degree bend in a. I just don't know if you know about it or could comment on that result.
Could you send me to, I think I don't see the link to that paper.
It should be in the chat.
Yeah, no, no, I don't see it.
Yeah, I also don't see it in the chat. I also don't see it in the chat.
Sorry.
Catherine, could you maybe while you put it in the chat, maybe give Keegan a chance to ask his question?
Yeah.
Because he had his hand up. Keegan?
Thanks again. I just wanted to ask, are you able to produce spectral index maps for the cosmic ray simulations?
Yeah, so no. Yeah, so in this formalism where I am putting, so it's a formalism where I have the cosmic rays in the same grid. So what we are working on right now is to have another formalism where instead you keep track of the cosmic rays with Lagrangian particles.
Okay, yes.
Yeah, and then I will have basically the energy distribution of each of the Lagrangian particles, and then I will be able to get the spectral index maps.
Okay, thank you very much.
Okay, now I see.
I see draining link to paper. Is that the paper you meant, Catherine?
Yes, that's the one. Thanks.
Okay. Oh, but I think I know which one you're talking about. Yeah, I need to log in to see the actual image. You're talking about one that is already disrupted, and that they suggested that there was a strong magnetic field on the upper part that was disrupting the AGN. Is that the one?
Yes, that's it. It's got a kind of weird 90-degree bend.
Yes. Yeah, I have seen these definitely. I'm just not aware if there is a merger happening there. Do you know?
I don't. I thought maybe you could comment, even if it wasn't a merger. But okay, no problem. Thanks.
Yeah, no, like bent sources in my simulation would mainly occur due to the merger dynamics. Yeah. So these will be, there are many things that have been suggested for these type of sources, but like this is one of them.
Oh, we have time for one last quick question, I think. Nadim, you had a second question?
I was just asking if these simulations are available for us to play around with.
Oh, We could definitely chat. They are not publicly available, but I would definitely be open to, collaborate if you want to take a look to certain things and even resimulate whatever case that you want to see further.
Thank you.
Excellent. Well, we have 1 minute left. Brian, you have your hand up. Do you have a quick 1 minute question?
Hi, it's Yoni. So the thing about Able 3376 is that there seems to be a merger happening sort of in the opposite direction of what the bend jets would suggest. So that's the thing about that. It bends against what you would think the ram pressure would be due to the merger.
I see. Okay. Yeah, well, that will be something that I'm not seeing. I will take a look to that more closely to see if another configuration of my initial parameters of the merger or something could somehow generate a tail that is in the opposite side. Thank you for telling me about that.
Excellent. Well, we're at the top of the hour, so I think it's time to let our speaker go. I'm sure you can email Paola if you've got more questions.
Yes,
Paola,
feel free to email me. And thanks a lot for having me there.
Yeah, thanks very much for joining us. It's been a great colloquium, and we look forward to having you again sometime.
Okay. Bye.
All right. Virtual applause.
Ciao.
Thanks again.
Bye. Thank you very much.
Thank you, man.
Cheers, everyone.
Thank you.